So here's the first acid definition we're going to learn about, the Arrhenius definition. And this is named after the Swedish scientist Arrhenius. I am not going to ask you to regurgitate the definitions of these different acid definitions. Okay, we'll refer to them, but mainly if you can recognize that it's an acid or a base, good enough. So under this definition, an acid is a substance that produces hydrogen ions in aqueous solution, and a base is something that produces hydroxide ions in aqueous solution. So HCl, hydrochloric acid, under this definition, is an acid because it produces hydrogen ions in solution. So here we have an illustration of HCl dissolved in water, and it separates into hydrogen ions and chloride ions. So it produces hydrogen ions. HCl is a covalent compound. It's not ionic, but when it's in water, it ionizes. It forms ions. Okay? Any questions? Hydrogen ions are very reactive. Let's think about, what is a hydrogen ion? It's a proton, right? So a hydrogen atom has one proton in the nucleus and one electron around the outside. You remove that electron and you have a proton. That's an incredibly tiny little thing, super reactive. You don't find them just by themselves. They are going to bond to water to form hydronium ions. So here we have our hydrogen ion, which is just a proton, and here we have a water molecule. This is the Lewis structure. Water molecule has two lone pairs of electrons, and so the oxygen can say, oh, you poor thing, you don't have any electrons. I'll share two of my electrons with you, and it will make a covalent bond with that proton, the hydrogen ion. As a result, this whole thing has a positive one charge and a different name because it's now a different thing, and it's called hydronium. There are other species that exist where you can have more than one water in there. We don't need to pay attention to those at all. So chemists will often use H plus and H3O plus interchangeably, because if we use H3O plus all the time, it makes our equations a lot more complicated, because then we have to account for the water molecule in there as well. And so what we need to understand is that when a chemist writes H plus, aqueous, this is in water, right? We understand that it's actually H3O plus, okay? Any questions? So a base produces hydroxide ions. Sodium hydroxide is a base because it produces hydroxide ions. So here we have sodium hydroxide, which is an ionic compound, a solid, and when you dissolve it into water, the ions dissociate. They separate, and you've got hydroxide ions. So hydroxide is one of the component ions in sodium hydroxide. We mentioned that acids neutralize bases and bases neutralize acids. When the hydrogen ions from an acid and the hydroxide ions from a base encounter each other, they'll make water. So then the acid and the base have been neutralized. They're gone. It's not acidic or basic anymore. The Bronsted-Lowry definition applies in wider situations. For one thing, the Arrhenius definition assumes that we're dealing with an aqueous solution. What if our solution is not aqueous? Then that definition doesn't apply. But the Bronsted-Lowry definition applies. And so this is focusing on the transfer of hydrogen ions. So an acid is a proton donor. Remember, a hydrogen ion is just a proton. So an acid, we learned it from nomenclature in Chem 1A, acid formulas start with H, right? And so they have a hydrogen and they can donate that to something else. So the acid donates the proton, the base accepts the proton. So we've got the hydrogen ion, and it gets moved from one thing to another. So HCl is an acid because when we put it into water, it donates a hydrogen ion to the water. So here we've got HCl, and we've got a water molecule. This hydrogen ion, which is just a proton, when this ionizes, that proton is very reactive, and it's going to immediately react with something around it. It's surrounded by water. It's going to react with the water. So we're going to get hydronium ion and the chloride ion. So, when we write HCl goes to H plus Cl minus, we understand that this is actually what's happening. But now we've got hydronium, and we have to have water in here. And sometimes it's important to think about what the water's doing, and other times we can ignore the water. So I think of this proton like it's like the smallest thing, right? Hydrogen is the smallest atom, and then you take the electron off, and the electron actually takes up most of the space in an atom. So this is incredibly small. I think of hydrogen ions as being like newborn babies, right? And so over here, the chloride is holding the newborn baby. The chloride's holding the baby. And when it dissolves in water, they separate. Well, you don't just put down a newborn baby and walk away. You hand them off to someone, right? So this is what's really happening, is that the HCl is saying, hey, could you watch my baby for a while? And giving the hydrogen ion to the water, and now the water molecule has the hydrogen ion, which makes it positive and has a new name, hydronium. So this is like babysitting the hydrogen ion. Any questions? What about bases? Well, so ammonia, NH3, is a base, and we might not recognize that immediately because it doesn't have hydroxide in it. If you see something like sodium hydroxide, potassium hydroxide, you're like, oh, it's got hydroxide in it. That's going to produce hydroxide ions. That's a base. This doesn't have hydroxide in it, but it can still produce them in solution. And under this definition, NH3 is a base because it accepts the proton. The acid donates the proton, the base accepts the proton. The base is like the babysitter, handing the kid off to the babysitter. So ammonia in water is going to accept a proton from the water molecule, and then it will become ammonium ion. It's got an extra hydrogen ion. And the water becomes OH minus, hydroxide ion. So ammonia does form hydroxide ions in water. It's just not obvious from its formula. But we can also think of it accepting a proton. The important idea is that acids and bases always occur together. So if you have a babysitter and a parent, right? The parent hands the baby off to the babysitter. If there's no babysitter, nothing happens, right? If you've got a babysitter and no parent, nothing happens. They are together, right? Acids and bases always occur together. So here, the hydrogen ion from water is being donated to the ammonia. Well, what is it called when something donates a hydrogen ion? It's an acid. So here, water is acting as an acid, donating a hydrogen ion to ammonia, the base. Down here, when we put HCl in water, now what's the water doing? It's accepting the hydrogen ion. Well, the definition of something that accepts protons or hydrogen ions is a base. So here, water is acting as a base, and HCl is the acid. So something like water that can act as an acid or a base, depending on the situation, those are said to be amphoteric. This prefix ampho is the same prefix used in the word amphibian, right? Amphibians live in the water and on the land. So amphoteric, it can be an acid and it can be a base. Let's look at what happens when we take that ammonia plus water equation and just write it backwards. Then we've got ammonium plus hydroxide ion making ammonia plus water. So this was the base when we looked at it in the forward direction. This is the acid now because it's got the hydrogen ion. It's going to donate that to the hydroxide. The hydroxide is acting as the base. So, this is an acid. This is a base. On the other side, we have this as a base, and this is an acid. The substance that was the base becomes the acid. And it's all about the hydrogen ion. So someone hands you a baby, you're the babysitter, you're the base. You could pass that baby off to someone else who's a babysitter for the babysitter, right? If you're handing off the child, then you're the acid. If you're accepting the child, you're a base. Any questions? So we talk about conjugate acid-base pairs. So if you have a base that has accepted a proton, it's done its function as a base, it becomes a conjugate acid because now it has a hydrogen ion which it could donate to something else. An acid that has donated a proton or had a proton removed is now a base because it could accept a proton. So a conjugate acid-base pair, these are two substances that are related to each other by the transfer of a proton. We do need to be able to recognize acid-base pairs. So NH3 and NH4 plus are a conjugate acid-base pair. What's happened is that if we add hydrogen to this, we get that hydrogen ion. We get ammonium. Water and hydroxide are also conjugate acid-base pairs. If we remove a proton from water, we get hydroxide. This is the acid, this is the conjugate base. So when we look at their formulas, the difference in the formulas is the number of hydrogens and a +1 charge. The acid has more hydrogens and a more positive charge. Here, this one has 1 hydrogen, this one has 2, this one's more positive, this is the acid. It's got the extra hydrogen. So we're looking at, who's got the baby? Who's got the hydrogen ion? Didn't mean to do that. This one is the base and that one's the conjugate acid instead of this being the base, the acid, and this being the conjugate base, just because we wrote this one on the left. So whatever you start with, you call that the acid or the base, and whatever it turns into is considered the conjugate. It could be backwards in a different situation. So in each reaction, identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and the conjugate base. Do we need to have the Bronsted-Lowry definition clear in our minds in order to answer this question? No, we don't. We need to be able to recognize an acid and recognize a base. So we look at this first one, we've got water and C5H5N. You're like, I don't know, I don't like that one. Let's skip that one and go to B first. Let's go to B. Oh, HNO3. I know that one, that's an acid, right? So this is the acid. The other thing, the other reactant must be the base. So this is an acid it's going to donate a hydrogen ion, it's going to lose a hydrogen ion, and it's going to become nitrate. And so this is considered to be the conjugate base. What happens to the water? Well, that's the thing that's receiving the hydrogen ion. So after it has received the hydrogen ion, it becomes an acid, and it's called the conjugate acid. It's the conjugate because it's on the product side. Any questions? The acid becomes the conjugate base. The base becomes the conjugate acid. Now we have to go back to A. We look at this and we're not, we're like, I don't recognize really, I know water can be an acid or a base, but I don't know what to do with this one. Look at the products. What happened here? Oh, the water lost a hydrogen. What does that make the water here? An acid. And what happened to this other guy? Oh, it gained the hydrogen, right? So that must be the base. So if C5H5N was the base, then it turns into the conjugate acid. Water was the acid, it turns into the conjugate base. Suppose you could also talk about a game of hot potato, right? Where you're passing the potato around. The hydrogen ion would be the potato. Who's got the potato? Do people still play that game? Yeah? Okay. Any questions? Okay, which of these is not a conjugate acid-base pair? What we're looking for is compare the formulas. Does one have one more hydrogen and is a little more positive, +1 in charge? So let's look at these two. What's different is this has H and now has a positive charge. This one doesn't have that H. These CH3s are the same for both, so they don't really matter. So is this a conjugate acid-base pair? Yeah. This could accept a proton and become that. That can donate a proton and become this. So that is, how about H2SO4 and H2SO3? What's the difference? Numbers of oxygens, right? This is not a conjugate acid-base pair. Look at the hydrogens. This one has 2 hydrogens. That one also has 2 hydrogens. You can't make one into the other by moving the hydrogen. So this is not a conjugate acid-base pair. How about this last one? The first one has a hydrogen, the second one does not. This is a 0 charge, and this is a -1. Because when you take the H plus off of this, right, then the charge of what's left changes to -1. Any questions?